Hi everyone, so today we're going to be talking about a special topic about water. Now most of us may have heard about water, what it does, and actually we're going to look at it as actually it's one of the most abundant compounds in living organisms. It forms up to about 60 to 95% of all fresh mass of living organisms. So because of that, we can tell that water is actually very vital. Okay, so in this video, we're going to discuss a few things here and there. We'll talk about the dipole nature of water. We'll talk about hydrogen bond formation. We'll talk about cohesion and adhesion properties, heat capacity of water, density, and so on and so forth. So firstly, we have to talk about the chemical structure of water. That way, we're able to understand why exactly is it being used as a solvent, or why exactly does it have a high heat capacity. So when we look at the dipole nature, first of all, I'll start by defining what polarity means. So when you look at polarity, this actually means an equal charge distribution over a molecule. Okay, so when we say something is of an equal charge distribution, so we're going to highlight this word, an equal charged distribution. So what exactly do they mean? So for us to actually understand this, they mean that in water, one end of the molecule is slightly positive, the other end is slightly negative. So this is the chemical structure of water. So one end is slightly negative and one end is slightly positive, like you can see. So because these are unequally distributed, this is what they mean, there's an equal charge distribution. So because they're opposite, they attract each other just like a magnet. If you have your north and this is your south, definitely there's going to be some force of attraction because they have opposite ends. So the same applies for this chemical structure of water. So this is our oxygen. Okay, so the electronegative end of oxygen is this part. In one molecule of water attracts the electrons of the hydrogen atoms surrounding water molecules. So water is able to attract another molecule of water. Because this is slightly positive, it's going to attract another slightly negatively charged and positively charged water molecule. So because of this is what we call dipolar nature of water. So each water molecule is attracting an individual molecule of water. So because of this, they form some kind of chain reaction, or rather a connection. Okay, now the other thing we're going to talk about furthermore in terms of the structure of water, what you're going to notice is that we have this oxygen bonded to hydrogen. Now, because this hydrogen atom is positively charged, as well as this hydrogen atom is positively charged, they repel each other in such a way that they form an angle of 104.5 degrees. So this is the angle that's between each water molecule. Okay, so having said that, next up we're going to talk about hydrogen bond formation. So what exactly is hydrogen bond formation? So the attraction between hydrogen and oxygen. So we have one hydrogen atom attracted to another oxygen atom. This is what we're calling hydrogen bond formation. So it's an attraction between this hydrogen and oxygen atoms of different water molecules. So for instance, if you have one water molecule here and I'm going to use a different color for another water molecule. So this is hydrogen that's going to be bonded to another water molecule. Okay, so this bond between these two is what we call the hydrogen bond formation. Okay, it's a formation between one hydrogen atom of one water molecule connected to another oxygen atom of a different water molecule. So when we say there are hydrogen bonds in water, this is what we mean. So this hydrogen is going to be connected to another oxygen molecule of another oxygen atom of a different water molecule. Okay, so all this is happening because of the dipole nature that we talked about in the previous slide. So this is exactly what we mean by hydrogen bond formation. Now the oxygen atoms of the water molecules and the hydrogen atoms of different molecules such as acids, we can find these hydrogen bonds in different in different chemicals. For instance, in alcohols, you know that all alcohols end with OH, right? So you know that between this oxygen and this hydrogen, there's a hydrogen bond formation that has actually formed. Okay, so keep in mind what hydrogen bond formation is, because it's going to come in handy. Okay, so we're now going to talk about water being used as a solvent. What do they mean? So for instance, you have a glass of water. So we have a cup of water, and I'm sure most of you are quite familiar. For instance, you have a spoon right here, okay, and on this spoon you have like sugar crystals or salt, and you know that salt is sodium chloride. Okay, so by it being sodium chloride, we definitely know that it contains sodium and chloride as individual atoms, and when they come together they form a compound that we are just calling sodium chloride. So water is a very good solvent for ionic substances. So we know that when we talk about ionic substances, these are compounds that have ions. We have anions and cations. Okay, the positively charged ions and the negatively charged ions. So when these two attract each other, the product is what we call, they form ionic bonds. Okay, just like you can see from this sodium that's positively charged, it attracts a negatively charged atom, and together they form an ionic bond. Now remember that water has a dipole nature, so you have this hydrogen as positively charged, oxygen is negatively charged. So what happens when you actually dissolve this salt in water? So let's just quickly erase our slide so that we can get a clear picture of what exactly we are talking about. Okay, so when you look at water, I'm going to draw it again. So this is one water molecule, right? I'm going to make sure I emphasize on the charges because it's dipole in nature. Okay, so because this water is slightly positively and negatively charged, when you dissolve something like sodium chloride, which is salt, your common table salt, what happens is that this chemical bond breaks. And how does it break? So because this is positively charged, this is negatively charged, each charge is going to be attracted to an opposite end. So for instance, the sodium, because it's positively charged, is going to be attracted to the negatively charged oxygen molecule. Okay, and because the chloride is negatively charged, it's going to be attracted to the positively charged hydrogen atom. So because of this, it causes this. If this was a salt crystal formed of sodium and chloride, this is what causes this to break down. The water molecules are going to surround this from all angles and break it down. Okay, so this is what's going to be happening. There will be so many water molecules attracted to that. So for instance, this is hydrogen. Okay, you have another water molecule there. So this is what's happening. This is what ends up breaking down chemical bond, this ionic bond. So hydration of the sodium ion is going to be by the water. For instance, this is your sodium ion, right? So there'll be so many water molecules surrounding this. Okay, so many such that the chloride will have no room to even bond with the sodium. Hence, this is how come things get dissolved. This is what we're talking about because of this slightly negatively charged. So these are negatively charged oxygen atoms that are being attracted to the sodium. So because this is surrounded by water, okay, this is surrounded by different oxygen atoms, the chloride is going to be here. For instance, this is our chloride. So the chloride is trying to bond back with the sodium, but it can't because it's the sodium atom is surrounded by so many water molecules. Hence, things actually get dissolved in water. That's why water is a very good solvent, because whatever is ionic is just break apart, because the water molecules will surround each individual atom of that compound that you're trying to dissolve in water. Okay, so another thing I need to mention is that when you look at salt or sodium chloride, it's a giant crystal. Okay, it's like a giant crystal lattice. Okay, so because of this you have, so this is like 1 grain of salt. So like we said, in order for this to break down, it must be surrounded by many water molecules. Okay, and that's how come each molecule breaks apart and gets an individual atom of that crystal. For instance, this oxygen molecule is going to get 1 sodium. Okay, so the more one molecule of this crystal is being surrounded by water, the more it's breaking apart. Hence, that is what we're actually calling as it dissolving. So water is a very good solvent of ionic substances. Next up, we're going to talk about water being a high heat capacity. So what exactly do they mean when they say water has a high heat capacity? Okay, so the specific heat capacity of water, let me just write the definition. So this is the amount, it's the amount of heat in joules that is required to raise the temperature of 1 kilogram of water by 1 degree Celsius. So water has a very high heat capacity, right? So from our definition, we're saying that the amount of heat in joules that is required to raise the temperature of 1 kg of water by 1 degree Celsius. Okay, so for instance, if this is your bowl of water or a beaker, so you have your tripod stand and this is a fire, right? So for us to raise the temperature of water at least by 1 degree Celsius, 1 kg of this water, okay, then for us to raise 1 kg of water temperature at least by 1 degree Celsius, this is what we call high specific heat capacity. So what do they mean? So having said this, they actually mean that it will take a lot of heat. Okay, it will take lots of heat for you to raise temperature of that 1 kilogram. So for instance, this is your beaker, you have water. Okay, there's a tripod stand, there's a flame there. Okay, for us to, the heat, this is our heat, right? The amount of heat that is required to make this boil, or rather to raise the temperature of water, for it to reach about 1 degree Celsius, is very high. This is what they mean. So because of this nature, it means that a large heat energy will result in relatively a very small degree of temperature. So it means, for instance, if this is a fire, right? There is so much fire. For you to raise the temperature of this water just to 1 degree, it will take, for instance, 1000 joules. Okay, just for it to raise the temperature of water to 1 degree. So it means you need so much heat to raise the temperature of water. Okay, so why is it that there's so much high specific heat capacity? It's because like we talked about the bonds in water, right? This hydrogen bond formation, it takes so much heat to actually break this bond. Okay, so because this bond is so strong, you'd have to apply so much heat in order to break it, just for water to be raised by 1 degree Celsius. So this is what they are talking about, and this means that water can variably not change in temperature so easily, right? So you look at the water in the ocean, the rivers. If water had a low specific heat capacity, this is to say, if it required only a small amount of heat in order for it to evaporate, it means most of our rivers would be dried up. But because water has high specific heat capacity, even when it's so sunny that day, it would require, there will just be like very few drops of water that are going to evaporate because of that nature. So because of this nature, the biochemical processes of living cells therefore take place within a narrow range, in a narrow temperature range. This is a narrow temperature range. Okay, so you look at the fish in the water, all these benefit from water. Okay, because it takes so much energy in order for this water to start evaporating and turn into gaseous state. Okay, isn't so much affected by heat, and because of this, it provides a very constant external environment for many cells and organisms. So organisms like fish, they're able to stay in water without being affected by the rays of the sun, because water won't easily evaporate, because if it did, many species would die. Okay, the next oh wow, looked like I actually talked about latent heat of vaporization as well. So latent heat of vaporization, I mentioned a bit, but I'm just going to go into further details. So latent heat of vaporization is the amount of heat energy required to vaporize a liquid. Okay, so the amount of heat energy required for water to actually evaporate. So remember, for specific heat capacity, it's the amount of heat that's required to just change temperature of water at least by 1 degree. That's specific heat, but here we're actually talking about heat that's required in order to rise, or in order for water to change from liquid to gaseous state. Okay, like we said earlier on, it means water has a high latent heat of vaporization, meaning that you need a large amount of heat. For instance, these are your flames. You need so much heat in order to change water from liquid to its gaseous state. As a result, and we know why this is, because it's because of those hydrogen bond formation that are found within water molecules. So as a result, water has an unusually high boiling point. Okay, so for water to boil, it must change at least about 100 degrees Celsius, sorry, not percent, 100 degrees Celsius. In order for water to boil, the temperature must be at least 100 degrees Celsius. Okay, because when it reaches 100 degrees, this is when it starts changing its state of matter from liquid to gaseous state. Okay, so the energy absorbed by water in order to evaporate, this energy, which we're calling heat energy, is what results into loss of energy from their surroundings. Thus, it causes a cooling effect of the surrounding. So for instance, you have a river, right? And there is so much water there. In order for this water to vaporize, okay, the water on the surface must reach at least 100 degrees and evaporate. Now, for this heat to come into the water, you have so much heat energy. Could be on dry land, from people that are passing around. It causes, there will be so much heat that will be absorbed from the surroundings. Okay, heat will be absorbed by water from the surroundings, thereby causing a cooling effect. That's what we call cooling effect. I'm sure most of you have noticed when you're close to any water body, it could be the ocean, the river, the seas, those places usually tend to be quite cold. Even if it's a stream, you're really cold. It's because water is being absorbed from different sources in order to vaporize itself. Okay, so through sweating and panting, mammals, so this is another point that I'm going to share. Let's just erase this. So when we look at human beings and animals like dogs, cats, so this is a person. Take it for instance, they go to the gym a lot, right? And they exercise. So when they start sweating from their pores, what happens is that when the heat is evaporating, when the heat is going, when the water from the body is coming out through sweat, it comes out together with the heat that it has absorbed. Hence, it gives a cooling effect. That's why people feel better when they sweat. It leaves their skin feeling cool. Hence, if you were just for a very long time, you would actually feel cold, because by that time the water would have absorbed most of the heat body. So next up, we are going to talk about density. So when we talk about water's density, it means that the density of water decreases at a temperature below 4 degrees. Okay, and because of this, ice tends to float. For instance, this is an ice cube, right? So it's found in a beaker of water. I'm sure you've noticed when you put ice cubes in a cup, they tend to float. This is because when water is frozen, or when the temperature decreases to up to 4 degrees, it then starts to become lighter. Okay, the density tends to decrease. Okay, when we talk about that, each water molecule in ice forms a maximum of 4 bonds. Okay, this is a water molecule. So let me just symbolize them with different color codes. So you have one water molecule here, another one here, and the fourth here. Okay, so each water lattice has about 4 bonds. Okay, there may be many of those 4 bonds. So this water molecule is connected to for instance, this one. So there's hydrogen there, another hydrogen there, hydrogen being attracted to oxygen. Okay, so this is what's happening. Hydrogen bond formation everywhere. Okay. Oh, sorry, let me just do that nicely. Okay. So this is what's happening. So because of these bonds that are forming, you remember that there will be repulsion between this oxygen molecule and these oxygen molecules, because they are of like charges, right? They're both negatively charged. So they will be spaced out, but there will be bond formation between hydrogen and oxygen and hydrogen right here. Okay, so because these two are spacing out, there's so much space that when water freezes up to a temperature of 40, like we have said right here, it causes water's density to actually decrease, because the amount of space that this mass is going to occupy is going to be so big. Okay, so for instance, if you throw a shoe in the water, right? Okay, sorry, but this is a terrible shoe. If you drop it in water, okay, we have splashes there. What you notice that this shoe is going to drown, or rather it's going to like go sink right deep in the water, right? This is a water body. But when you throw a leaf, okay, this is a leaf, it's because its weight is distributed evenly in such a way that it enables a leaf to just float on water like that, okay, without actually sinking. So because of these spaces, it's like water is evenly distributed. The water molecules are evenly distributed in water at this temperature, okay? Because when they're losing, when water is losing heat, the amount of movement that water molecules make around each other decreases to a point where they freeze in such a state, okay, enabling it to actually float. So this is why water actually, when it reaches a temperature of 4 degrees, it tends to float in liquid water, because liquid water has a different density. It's more dense than ice. I'm sure you've noticed in the North Antarctica, there are situations where you have a huge iceberg right on top of water, or a very small iceberg, then there's a bigger one underneath, and you may never really know, because you may think this is all you can see, when actually beneath the water there is more ice. Okay, so this is what we are talking about. So each water molecule forms about 4 bonds, but some books mention about 3 to 4 bonds, okay, about 3.4 bonds in other water molecules. So since to float, it forms it forms at the surface of water first and at the bottom last. So when it starts losing density, or when they're breathing, that water starts floating on top, and then it's turned into ice. For those countries where it's quite cold, they have like ice. I'm sure you've heard of ice skating. So the water tends to float at the top first, and then it forms ice at the bottom last. So water is forming ice right here at the top. It means all the fish that's underneath are protected. Why? It's because the water here on the middle, okay, for instance, if this is a fish, the water here in the middle is relatively warm as compared to the water there, because now the ice at the top is acting as a shielding effect, okay? It's preventing more heat from evaporating from the water. So fish and aquatic animals tend to survive at a despite water like being in such a state, okay? So the next up thing we're going to talk about is cohesion and adhesion, surface tension. So what do they mean when they say cohesion and surface? So cohesion is a force. So let me just write it down here. So cohesion is the force which makes similar molecules. The force which makes similar molecules stick together. Okay, so the word cohesion, from cohesion. Co means that two things that are involved. So you have one water molecule and another water molecule. We said these two water molecules are connected, right? You have hydrogen being connected there, forming hydrogen bonds, right? And this hydrogen is connected to that. So these are what we call cohesion molecules. Water molecules are able to stick to one another or to each other because they are cohesive. Okay, so it forms a very thin skin on the surface of water. Okay, so I'm sure you've seen those insects. Oh my, how can I draw this? So this is an insect, right? For instance, if this is an insect with its antennas there, it's able to walk on water. It almost looks like things can walk on water. It's because there's a thin skin that's made. So one surface molecule, it's like people that are holding hands. Okay, they form a chain. So if this is the insect coming to step here, the bonds are so strong that they form like a very thin surface on which these insects or leaves are relatively able to float on them. Okay, so this is what happens. So the high cohesion of water molecules helps the movement in cells. You have this is your tree or your plant. You have what we call the xylem and the phloem. The xylem that carries water, the phloem that carries nutrients around the plant. So the xylem carries these water molecules. How are they going to be able to move? Okay, in order to reach other branches and other leaves, it's because of the cohesion forces. Okay, water attracts its fellow water molecules, so it's going to move like that all the way until it's able to reach its target. So in addition, many small so adhesion is important in the movement of water along the walls of vascular tissues, like we have talked about, and even along blood vessels in the body of a human being. So this is what we meant. So the cohesion is the force which makes similar molecules stick together, right? So these are able to stick together, and this is what helps in movement of water in cells, especially in the translocation of water, so in the xylem of plants. So in addition, many small aquatic organisms are able to float, like we said here, this example or small illustration. So the next thing we'll talk about is adhesion molecules. So remember, cohesion is the ability of molecules to stick to other molecules that are alike. When we look at molecules in terms of water adhesion properties, we're going to look at the attraction between water molecules and other different substances. So when you talk about adhesion, this means that water is being attracted to other substances, unlike cohesion, where there's a force of attraction between substances quite alike. So let me give you an example. So this is a bottle, right? You have water. Notice that the water easily sticks to the walls of this bottle. Now, because it sticks to this wall. This is what we call adhesion, from the word adherence. If something is adhering, it means it's sticking to that place. So this makes things wet by sticking to their surfaces. For instance, you put a cloth, okay, you put a dress in water, it's going to stick to the water, it's going to make it wet. Hence, this is what causes things to actually get wet when you dip them in water, because water is highly adhesive, important in the movement of water along the vascular tissues in plants and along blood vessels in mammals. So sorry, we mentioned that point in the previous cohesion. We actually needed to mention it here, adhesion, because it's adhering to the walls of these. For instance, this is a blood vessel. You have red blood cells and whatnot. These red blood cells are literally moving in blood because there is a percentage of water that we find in plasma, right? Which is a liquid through which blood vessels pass. So for instance, this is a blood vessel. So let me label it here. This is our blood vessel. This is our xylem in a plant. Okay, so this is like a tube. So these are the walls of the plants. Water molecules are going to stick there, okay? And because they're sticking, they're going to be moving in that action. So this is what helps them to move along blood vessels. Then the next, we're going to talk about the capillary action of water. The capillarity in water, which is our last point. So this is the ability of water to flow upwards in narrow vessels. Narrow vessels like blood vessels. Remember, adhesion was saying the water molecules are just sticking to other substances, but capillarity, they gain ability to start moving along that vessel. So like blood, water starts moving in an upward manner, or in a direction in which that blood is moving. This is what we call the capillarity action. Capillarity action of water is due to the action of cohesion and adhesion forces. Okay, so in capillarity you have cohesion plus adhesion, forces that work together in order for water to move. So for it to move, firstly, the water molecules have to be cohesive. They must attach to one another. Okay, for instance, this is hydrogen. This is a hydrogen bond connected to another oxygen molecule, atom, I mean. Yeah, so this is what's happening. So they must stick to each other, okay, and they must stick to the walls of that container. Okay, so when this happens, water is able to move or be able to be translocated from one end of that to the other. Hence, this is what we call the capillary action of water. So having said that, what you notice is that these forces, it actually occurs when the forces of adhesion in that vessel walls are stronger than the forces of the cohesion between the liquid molecules. So the narrower the tube, the higher the capillarity. So the narrower the tube, for instance in blood vessels, like the capillaries, the narrower they are, the more capillarity. So blood moves a bit more quicker there. Though in cases, for instance, this is a capillary tube and another one of a different volume. What you notice is that if they have the same liquid, there will be more liquid that's going to fill in this capillary tube that's narrow as compared to this one that's bigger, and even less in the one that's more bigger, because this is a tight space. Molecules are tightly packed, hence the more tightly packed they are, the more the force pushes them upwards, hence having higher capillarity, thereby making liquids be pulled higher and higher. So this is what we mean by the capillarity of water. So in summary, just going to review what we talked about water and how vital it is. Talked about the dipole nature of water. Talked about the hydrogen bond formation that's found within water. We also talked about how water is actually a solvent. Next up, we talked about heat of vaporization, as well as density, cohesion and surface tension, and adhesion properties of water, as well as capillarity. Okay, so this was all for water. I hope you enjoyed.